Similarly, in this question also v theta and vr is 0. But the velocity in z direction is not 0. This is non-vanishing velocity vz. Because our flow is laminar and in z direction. So we are solving this equation by a Navier-Stokes equation in cylindrical coordinates. So we have three equations of motion: r equation of motion, theta equation of motion, and z equation of motion. But the recently you say that the r equation of motion and theta equation of motion is 0. So you are only using the z equation of motion. Equals to minus dou p by dou z plus mu 1 by r d by dr r dvz by dr plus 1 by r square dou square vz by dou theta square plus dou square vz by dz square plus rho g z. This is z equation of motion. This question is given that v theta and vr is 0 and vz is non-zero. So by solving this equation, we will put v theta equal to 0, vr equals to 0, and vz is non-zero. So we have neglect some terms, like this is become a 0 due to steady state. This is become a 0 due to vr is 0. This is become a 0 because v theta is 0. This is become to 0 because vz is 0. So finally we have get the equation. There are two terms also neglecting, that vz is not changing in theta direction, that's why this term is also 0, and our dvz is not changing in z direction, so this term is also 0. So we have only these terms. But by combined pressure, by this equation we have only this term, and also we have further solution of this term. We have to combine pressure form. So we have forming So we have get this term. So this is our equation by solving the Navier-Stokes equation. So we have four boundary conditions. Boundary condition 1 is z equals to 0, p is equal to p naught. Second is z equals to L, p equals to PL, and r equals to R, Vz equals to 0, and r equals to 0, Vz is finite. There are four boundary conditions. So we have to solve further. So this is equation for us. So solving this equation further, we have get dp by dz is equals to 1 by r d by dr of r dvz by dr. So we have take this equation is equals to the C naught. So solving further, we have get the solution of this differential equation. So solving this differential equation, apply both sides by r and multiply the both sides by r. So if you are multiplying both sides by r, so we have d by dr r dvz by dou r is equals to C naught into r. So solve this differential equation by integrating once. So if you are integrating once, so r dvz by dr is equals to c r square by 2 mu plus c1. So c1 is our new constant. So further we have solved this equation by divide by r. So if this equation is divided by r, so you have see that this r is, so this r is cancelled out and this r also cancel out, but there are only one r. Finally, we have the equation dvz by dr is equals to cr by 2 mu plus c1 or this or divided by r. So further we solving again integration. So you are double integration in that question. So if you are integrating this equation, we get the Vz r is equals to c r square by 4 mu plus c1 ln r plus c2. So this is same equation as per we are solving flow through a circular tube. But so this is our final equation. So we are applied boundary condition on this equation. So first boundary condition assuming no slip at cylinder walls. So at r equals no slip at both cylindrical walls. At r equals to r1 and mu z equals to 0. At r equals to r1 and mu z equals to 0. And at r equals to r2 Vz equals to 0. Use these two conditions to solve for C1 and C2. So further we are solving the C1 and C2 to our final form of velocity profile. So we are getting the velocity profile like that. So solving further, we have get the velocity profile is Vz in r direction is equals to c by 4 mu r square minus r2 square minus r1 square ln r by r1 divided by ln r2 by r1 minus r1 square. So this is our final velocity profile. This is the typical velocity distribution in angular region. So we have solved all questions flow through an LNS. So this is some key points of that question is use cylindrical coordinate due to symmetry. We have used a cylindrical coordinates because so in this question we use a cylindrical coordinate due to symmetry. Only axial pressure gradient matters. Third one is Navier-Stokes simplifies to an ODE in R. Fourth one, apply no slip body condition at both cylinder walls. That's why we are getting this equation. Finally, result is a logarithmic parabolic velocity profile. So solve this question by Navier-Stokes. That's way. Welcome back. In this video, we will explore a classic pneumatic problem, the flow of the falling film, using a powerful Navier-Stokes equation. This is a crucial application like chemical reactor, heat exchangers and film condenser. We'll derive the velocity profile, shear stress distribution and film thickness under gravity. Let's dive in. So, we have a question of falling film. So our topic is flow on a falling film. So our question is consider a flow of a liquid down. Flow of a liquid down and inclined flat plate of length L and width W. The inclination angle of a plate is beta. And thickness of a film over a plate is kept constant. This is delta. If delta is very small as compared to L and W, derive the equation for velocity and momentum flux profile. And also, hence they develop the equation for maximum velocity. So we have the question is derive the equation for velocity and momentum flux profile. So assume the liquid density is constant and viscosity is also constant. Neglect all end effect because of disturbance. So we are making the diagram of this question. We have plate this is plate, this is inclination on the plate. There the liquid is flowing over the plate. The distance is L from there to there and the beta is angle between the inclination angle. So there is a small hole for liquid in the film, and the direction of gravity is downwards. So we have tackled this question by a navier equation. We consider a film is incompressible, Newtonian liquid flowing steadily down a vertical flat plate or under gravity. The film thickness is delta, and we'll assume the flow is fully developed and two-dimensional, meaning variation in z direction are negligible. So our further assumption is let's outline the assumption. Our first assumption is steady flow, laminar flow, secondly, their liquid is incompressible and Newtonian fluid. And Newtonian fluid. Thirdly, the gravity is the driving force. Fourth assumption is no pressure gradient along the flow. No pressure gradient along the flow, and no pressure gradient along the flow. Then after, the flow is only in x direction, velocity u y. The flow is only in x direction, then our velocity is v of y. No slip boundary condition at the wall. This is common condition in all three cases. No slip boundary condition at the wall. And our last assumption is shear stress is zero at the pre-surface. Shear stress zero is at the pre-surface. So finally, our assumption is completed. So further we are solving the question. So this question, flow of a falling film, is solved by a navier equation. Firstly, we have see that the navier equation is three types: the cylindrical, Cartesian, and spherical. In this question, we will use a Cartesian form of navier equation. So the Cartesian form of navier equation in x direction for incompressible flow is the navier equation in the x direction for incompressible flow.